Hey guys, welcome back to my channel. Today we are looking at AQA A-Level Chemistry, Inorganic Chemistry Part 2. If you haven't watched Part 1, feel free to go check that out on my channel. But today we'll be looking at period 3 elements, transition metals, and reaction of metal aqua ions. So before we jump in, like I always say, I'd really appreciate if you subscribe to my channel. You can find a lot of other AQA A-Level Chemistry videos on there. I'll be uploading some more as well, depending on when you watch this. And I've also got sociology and psychology on my channel already. So if you find them useful, if you're studying those other subjects as well, make sure to check them out. And yeah, if you have any questions at all, feel free to comment below, and either myself or your fellow students will get to them. So firstly, looking at period 3 elements. Firstly, looking at metals, so sodium and magnesium both react ionically to form positive ions. Sodium is more reactive than magnesium as it only has one electron to lose, therefore less energy is required. Rate of reaction can be increased by using steam versus water as there is more energy present. Obviously, gas particles are a lot more chaotic and energetic than in liquid. Then when it comes to oxides, so period 3 elements react with oxygen to form oxides, with each element in their highest oxidation state. Sulfur can also react to form SO3 with an oxidation state of +6, but this requires high temperatures and a catalyst. So here's some key ones to remember just in the bottom of that table, or bottom in the oxide column. So you can kind of see the general kind of oxidation states of them. And in the top left corner as well, just to note, there is a nice little table of the oxides with kind of their structure and bonding, their relative melting point, and how reactive they are. These are really, really important to remember, and they'd be really, really useful. Apologies, I couldn't get it bigger, but I couldn't fit it on the screen. So yeah, I hope you can see it okay from there. Then how period 3 elements react with water. So ionic oxides combine with water to form alkaline solutions with a pH of around 10 to 14. And the simple covalent oxides of sulfur and phosphorus combine with water to form acidic solutions with a pH of around 0 to 2. When in solution, these acids dissociate into H+ ions and ions of conjugate base. So you can kind of see here, along all of these slides, there are lots of example equations to kind of show you what this would look like. So make sure to pay attention to them. Obviously, it's a lot easier for you guys to kind of see them. There's not much in particular for me to talk through with them. Then for acid-base reactions, so basic ionic oxides react with acids to produce a salt and water in a neutralization reaction. Acidic covalent oxides react with bases to produce a salt and water, again, a neutralization reaction. And the bonding in aluminium oxide is partially ionic and covalent, meaning it's insoluble in water as the ions don't dissociate, but can act as an acid or a base, which is known as being amphoteric. Now, moving forward to transition metals, there is a lot of content on transition metals, so we've got a few slides on this. So transition metals are elements in the D block of the periodic table with a partially filled d orbital and lose electrons to form positive ions, with the s orbital electrons being removed first. Again, like always, apologies for any spelling errors. All transition metals have similar physical properties, including atomic radius, high densities, and high melting and boiling points, as well as special chemical properties. So this includes forming complexes, forming coloured ions, variable oxidation states, and good catalysts, which we will continue to discuss. So complexes, first up, consist of a central metal ion or atom surrounded by ligands, which are molecules or ions with a lone electron pair that is able to form a coordinate bond to the central metal ions by donating this electron pair. Example of this is chlorine ion, water, and ammonia. You can see an example of this complex kind of idea in the top of the presentation. The coordination number is equal to the number of coordinate bonds formed around the central metal ion. So silver has a coordination number of 2 and platinum has 4. The ligands of H2O and NH3 are similar in size and are both uncharged, and so can be exchanged without a change in coordination number via ligand substitution reaction. So again, you've got another example here. With copper complexes and NH3 in excess, this substitution is incomplete and the complex formed has a combination of water and ammonia ligands. This complex ion product forms as a deep blue solution. The chlorine ion ligand is much larger than the water and the NH3 ligands, meaning substitution with this ligand results in a change of coordination number for that complex. Complexes with just chlorine ligands also always have a coordination number of 4, producing a tetrahedral shaped complex. Then there's different types of ligands. So you've got bidentate. These are able to form 2 coordinate bonds to the central metal ions as they have 2 lone electron pairs. These 2 common bidentate ligands, so in the table in the top right, can replace 2 unidentate ligand, but the coordination number remains at 6, and 6 coordinate bonds still form. Then we have multidentate ligands, which are able to form up to 6 coordinate bonds to the central metal ion as they have multiple lone electron pairs. The most common is EDTA, and I'm not even going to try and pronounce the actual meaning of that. But this forms 6 coordinate bonds in a ligand substitution reaction, and you can see the example reaction in the middle there below the table. Then you've got heme, so heme, I think it may be, or heme. That would make sense, seeing it's the same spelling as hemoglobin. But so heme is a component of hemoglobin. And it's another multidentate ligand consisting of 6 coordinate bonds around a central Fe2+ ion, and its shape and structure allows it to transport oxygen around the body. So this is the structure you can see in the bottom right of the presentation. Carbon monoxide is toxic to humans as it replaces the oxygen in the heme complex. That's not meant to be ham, that's meant to be heme complex, thus preventing it from being transported around the body. A positive entropy change is favourable as it means more stable complex is being formed, and so it's also favourable to have more moles on the right than the left-hand side of the reaction, which is achieved by substituting unidentate ligands with bidentate or multidentate ligands, known as the chelate effect. The greater the entropy change, the more negative the free energy change will be, and so the reaction is more favourable. And finally, the enthalpy change for ligand substitution is very small, as the bonds being formed are very similar to the bonds that are broken. Therefore, overall enthalpy change is near 0. Now, transition metals can have very different shapes. So we've got 7 different types of shapes here. So firstly, you've got the octahedral complex. So transition metal complexes with water and NH3 ligands commonly form this with a bond angle of 90 degrees. Then we have the cis-trans isomerism, so shown by octahedral complexes with different types of unidentate ligands. Ligands of the same type can be next to or opposite each other. The trans isomer has 2 of the same ligands opposite each other, and the cis isomer has them next door to each other. Optical isomerism, so this is shown by octahedral complexes with bidentate ligands and are mirror images of each other. All of this is a lot easier to understand, I feel, when you can actually see the pictures, so I hope they are big enough and you can see them properly. But again, like I always say, if you have any questions at all, please just put them in the comments below and I will get back to you as soon as I can. Then we have tetrahedral complexes. So when complexes form with larger ligands, such as chlorine, they form tetrahedral complexes with a bond angle of 109.5 degrees. These can also show optical isomerism. Next, we have square planar complexes. So platinum and nickel complexes form in a square planar shape that consists of 4 coordinate bonds with a bond angle of 90 degrees. Then we have linear complexes. So silver complexes always have a linear shape with 2 coordinate bonds around the central metal ion with a bond angle of 180 degrees. The example below is known as Tollens reagent, which we'll look at in a little bit soon. Then finally we have cisplatin. So this is the cis isomer of a square planar complex of platinum and commonly used as a cancer therapy drug. So cells in the natural world are known as chiral, so only one isomer of the drug will be the correct orientation to fit the cell. However, cisplatin can cause serious side effects, for example, hair loss, but because of this, it then usually tends to be used in small doses to try and avoid these side effects as much as possible. Now, transition metal ions can be identified by their colour, which depends on the coordination number of the complex, type of ligand bonded to the ion, and the oxidation state. Colour arises because of how substances absorb and reflect light, so you can kind of see how this works in the top left corner. So when white light shines on a surface, then some of the wavelengths of light are absorbed, but the remaining wavelengths are reflected and transmitted to the human eye, and these reflected wavelengths correspond to a specific colour, which is then observed by the human eye. Electrons in the d orbital exist in a series of energy states. When they are given energy, they move from ground state, n equals 1, to a higher energy state called an excited state. So you can kind of see the basic structure of these energy states and how they're described, drawn in the top right corner. The change in energy between these states corresponds to a wavelength and frequency of light. Colorimetry is an analytical technique that uses the absorption of visible light to determine the concentration of coloured ions by measuring absorbance. So this again is the bottom little diagram. You can kind of see the actual structure, how the layout of this would work. And apologies, I forgot to mention if you look above this colorimetry image, then you'll see an equation which basically helps you to work out the energy change with the energy state diagram, which is really, really useful. I'm not entirely sure if you get that in your exam. I'm hoping you do. But yeah, make sure you double check what equations you have in the exam. And then from that, the calibration graph is produced by measuring solutions of known concentration, which can then be used to calibrate the colorimeter on a graph of relative absorbance against concentration. This graph can then be used to determine the concentration of an unknown substance. Apologies if I stutter at all. I'm trying my best. Then following from that, so one of the key chemical properties of transition metals is their variable oxidation states. So vanadium has 4 possible oxidation states, which can be produced from the oxidation of vanadium by zinc in acidic solution. So you can see here in the right-hand table exactly what oxidation state it is, the actual formula of this, and then also what colour it would produce. So oxidation state for +5 is yellow, all the way down to +2 is violet. The pH of the reaction determines whether a transition metal is oxidized or reduced. For ions to be reduced, acidic conditions are required, but to be oxidized, they need to be alkaline. Now looking a little bit more at Tollens reagent, so here you can see the actual structure of this, like we spoke about a little bit earlier when it came to the shapes. This is reduced by aldehydes to form silver atoms, seen as a silver mirror, and so is used as a test for aldehydes. And just in the bottom right here, there's also 3 important redox titration reactions, which are really, really important for you to know, because you may need to be able to recite these and have a knowledge of this if you are discussing transition metals in your exam. Then looking at catalysts, so transition metals are really good catalysts, but essentially, just as a little refresh, a catalyst is a substance that speeds up a rate of reaction without being used up by providing an alternative route with lower activation energy. And there are 2 types of catalysts. So you've got heterogeneous. So these are catalysts that are in a different phase or state to the species in the reaction. An example is the Haber process, which uses the solid ion catalysts. Transition metals make good catalysts due to their variable oxidation states. Electrons are transferred to produce a reactive intermediate and speed up reaction rate. An example is contact process using a vanadium oxide catalyst. Heterogeneous catalysts can be poisoned by impurities which block the active sites and prevent adsorption. Therefore, bonds of the molecules remain strong and catalyst has no effect. These impurities can lead to increases in chemical production costs as the catalyst has to be replaced or cleaned regularly. Just to clarify, when I'm talking about activation sites, so this is kind of about what you see on the bottom of the presentation, so a little diagram of how the catalyst is kind of how the catalyst is actually a part of the reaction without actually being a part of it, if that makes sense. But essentially the activation site is the key part to how the catalyst can be a part of the reaction. Then we've got homogeneous catalysts, so these are in the same phase to the species in the reaction and works by combining with the reactants to produce a reactive intermediate and changing the reaction path. A solid catalyst works absorbed molecules onto an activation site, onto an active site on the surface of the catalyst. These active sites increase proximity of molecules and weaken the covalent bond in the molecules so that reactions occur more easily and rate is increased. The strength of this depends on the type of catalyst, so iron, cobalt and nickel are best as they are relatively cheap and increase the rate the most of all period 4 transition metals. Then finally for catalysts you have autocatalysis. So one of the products can act as a catalyst, so over time as product increases, so does the rate of reaction, which I think is really, really interesting. But yeah, so that is it for catalysts. Then looking at reactions of metal aqua ions, so metal ions become hydrated in water with H2O ligands around the central metal ion. The reaction of 4 major metal aqua ions have to be known. So this is iron 2, copper 2, iron 3 and aluminium, which form coloured precipitates. Just to note, over the next couple of slides, all the colours of the equations will refer to the actual colour of the reaction. So it's really, really important that you kind of not only learn the reaction, but also learn the actual colours that they are as well. When these ions are in solution, they are acidic, so metal ions that form 2+ ions, iron 2 and copper 2, form weak acidic solutions than those that form 3+ ions, so iron 3 and aluminium. Therefore, 3+ ions dissociate more and a stronger acid. Solutions of these metal ions react as acids with sodium hydroxide in a neutralization reaction to form a salt and water. These reactions hydrolyze the metal ions to form colour precipitates. So again, at the top you can see, so for iron 2 this is green, for copper 2 this is blue, for iron 3 this is purple, and then for the aluminium it's just it's colourless, it doesn't have a colour to it. Then there's also such a thing as amphoteric salts, so like we spoke a little bit earlier about amphoteric. The aluminium salt can act both as an acid or a base, so it's amphoteric. So sodium hydroxide is added in excess. The salt acts as an acid and hydrolyzes further. Reactions with ammonia, so solutions of these metal ions react in a similar way with aqueous ammonia to form a salt and ammonium ions. And when ammonia is added in excess to these precipitates, the copper 2 salt undergoes ligand substitution to form a deep blue solution. Then finally, so reactions with sodium carbonate, so solutions of these metal 2+ ions react with sodium carbonate as acids, forming insoluble carbonates and water. Solutions of the metal 3+ ions act as a stronger acid, meaning they react with sodium carbonate to form a salt, water and carbon dioxide. And reactions with chlorine ions, so all metal aqua ions undergo ligand substitution reactions to form tetrahedral ions with 4 chlorine ligands, which occurs when they react with concentrated hydrochloric acid. So that is everything for inorganic chemistry. I lost my words there. Apologies for any stuttering today. I've really tried my best. Yeah. Please don't comment about it below because I'm alright, thanks. But I hope you found this really useful. Please let me know if you have any questions at all. And of course, like always, subscribe, like the video, and I shall see you soon.